Hello everyone, today we discuss contest 5. Difficulty, I would say, is okay, except the last problem. So I spent like, you see, here's my status. So I spent like, to start here, no, I made breaks, so it's okay, it was less than an hour with all the breaks I made to solve first 7 problems and then more than an hour to solve the last one. Last problem is surprisingly hard. I didn't expect it to be that hard, actually. So it turns out it's actually last problem is problem E of Div 2 contest. So it's the most difficult problem of Division 2 contest. So and I usually try to aim on some Division 3 difficulty. So last problem is a little bit more difficult than usual. But again, one person solved that problem. So what's your rating now? It's 17. It's surprisingly smart for this rating. Okay, so we will discuss all the problems, then we get to the last problem, and I will tell you how I get to this point. So it was actually fun to solve this problem. I made a lot of mistakes, and then had to find all these mistakes. We will get to it. Okay, let's go. Problem 1 is okay. First few problems are pretty simple. So first problem, you need to solve this equation. It's called Diophantine equation, if you didn't know. So you need to find numbers x and y such that xa plus yb equals n. Yeah. So you know numbers a, you know number b, you know number n, and you need to find numbers x and y. It's called Diophantine equation. Not that important. You can solve it in log n time complexity if you know Euclidean algorithm. Okay, it's home task for you. If you don't know how to solve Euclidean algorithm, you can do it in log n time complexity using Euclidean algorithm. It's not required here. Here, what is required is actually to find any solution for this problem and for some small numbers. So all numbers n and b are pretty small. So instead of using some special algorithm, you can use some simple brute force. So you can find any number x. So x should be at least 0 and at most 10 millions, yeah, 10 power 7. So I can check all possible values of x. If I know value of x, then I can find number of y. And if this number is integer, then I found some good pair. Okay? Just check all possible numbers x, find number y. If it satisfies all the constraints, then you find the solution. Pretty simple. So just let's go. Let's again speed up a little. So we don't wait. So again, I look for all numbers x. Here I do it carefully. So I do numbers x only until x multiplied by a is greater than n. So if xa is less or equal than n, then it's some valid value for x. Then no value for x. I calculate number y. Here you see. So if it is integer, so if this number is divisible by b, then I return yes and return this. Okay, so okay, I don't know why, so I need to copy this again. That's it. That's basically the whole solution. Yeah, pretty simple. Just make one simple loop and find it. And again, so it happens a lot in programming competition, especially in the easier problems. So when you have some type of equation, yeah, and your first impression is to solve this equation like mathematicians do. But let you think, okay, you don't need to solve it like mathematicians do. You need to solve it like programmers do, yeah? And the way programmers solve equations, just a lot of times it happens, then instead of just having some analytical solution of the problem, you just make brute force over all possible solutions and check which one actually fits to your equation. That's what happens here. So the only trick is that instead of checking all possible pairs of x and y, that will be too slow. Yes, you can check only one. So you have two variables. You brute force one, and then analytically find the second one. Yeah, that's a little bit so mix of mathematical approach and programming approach. But overall, that's it. That's problem. That's problem A. Nothing really interesting here. Just test it, submit it, wait a long of time for code forces to submit. That's it. That's problem A. let's go to problem B. Problem B is actually mostly implementational. So no algorithms here, no mathematics here. You just need to read all this block of text, understand what's going on, and then implement it. Okay, there is small algorithm in the end, but it's pretty simple. So what you need to do, you have a ship which can transfer k items, and you need to choose from where to where you transfer these items, and what is the maximal profit you can get. Okay, code force is very slow today. Let me show you. So you transfer items from one planet to another planet. Number of planets is small. You see number of planets like 10. So you can just check all possible pairs, like 100 possible pairs. Okay. No, again, you read up to this part and see that all constraints are kind of small. So you don't care about time complexity that much. Sometimes you do, but not that much as usual. Yeah. So you need to transfer items from here to here. For each items, you know the cost of buying this item, ij. So let's say planet X and planet Y. Yeah. So you X. So if you transfer item I, you have AXY to buy it and B YI to sell it. Yeah. So this is cost of buying. This is cost of selling. So if you buy one item, buy it here, sell it here, you get income like BYI minus AXI. Yeah. So this is your income. Yeah. And it's easy to calculate this income for any pair. So we have like 10 square possible pairs of planets. For each pair of planet, you need to calculate for every item. You have 100 items. So you can easily calculate it for everything. Yeah. So you can calculate this value for everything. Yeah. Not a big problem. Now you need to choose which items to take. And it's easy to see that you take the items with maximal possible profit. Yeah. So you take all these items, sort them by this value, and take the items of maximal profit. Now for each item, you also know the number of items. You see here. So you also, I believe you can do it, but it's up to 100. You can do multiply by another 100. You can just pick them one by one, actually. But I do it carefully, actually. I do it in blocks. So I sort all types of items in decreasing order by the income. Yeah, and profit, by the profit. So I sort all items by the profit in decreasing order and then take them in blocks. So I take block of the same items, the maximum amount I can do. So it's boring, this boring, this boring. So I'm just reading data. Yeah. So here I checked some pair of planets. So planet I and J. Okay, in this implementation they called here. Now I will get all this. So I will get all these items, sort them, and put them in this array. You see. So I take all the types of items. Yeah, here. Okay, I double check that. Okay, so B is less than A because I cannot put the items to the same planet. So I didn't check that I is not equal to J here. You see. So I double check that it's allowed actually. No, it's not allowed. It doesn't specify it in this problem if it is allowed or not. But if B is less than A, it means it just doesn't make sense to put the items to the same planet. Yes, you will just sell them with lower price than you bought them. Okay, so here, so here I iterate for all pairs of planets, iterate for all items, and put to this array my profit and number of items. You see, this have pair of profit and number of items. Then I will sort this array just in decreasing order. That's the plan. Now, I go in this order, in decreasing order by the profit, and greedily take as many items as I can. Yeah, that's the plan. So kk is number of items I can take. So initially it's equal to k. Then I will take these items in decreasing order. Every time I take maximal possible number. Maximal possible number is either kk, so maximal k, or y. So y is number of items I have, so it's the second element of the pair, see? So when I put it here, it's this value c. See, it was here, and then I put it here. So I have y items of this type, and I can take up to kk. So I can take minimum of these two values. Yeah. Now, if the profit is positive, if profit is negative, you don't take this item. Yes. If profit is positive, then you increase your sum by this amount and decrease number of items you can take. And that's it. That's it. That's the whole solution. Can you show me the solution? Okay, now I spend a lot of time just to submit. Okay. Okay, let me actually open the problem here. Summation, so problem B, because it's not very short, so we can. Okay. Okay, let's copy it. Not here, here. Okay, so that's the whole solution. So I read the data, iterate all pairs of planets. For each pair of planet, I iterate all items. For each item, calculate the revenue, the profit I can get, the number of items, put these pairs into some array, and then sort the array by the profit. Yeah, and then I will take these items in decreasing order of the profit. Just simple greedy algorithm, yes. And I do it like this. So these things there. So again, I take this pair, so I put them in x and y just to make things more complicated. Yes. So x is this value and y is this value. Yeah. So x is my profit and y is a number of items. Yeah. Every time I calculate how many items I can take, it's minimum of how many items I have and how many items I can take. Yeah. Now I take p items, so it will increase my total profit by this, and it will decrease number of items I can take by this. Yeah, and then just calculate maximum of all possible pairs of planets. So for each pair of planet, I calculate maximal profit, then take maximum of all these values. That's it. So every step is kind of logical. So maybe this step is the most difficult one. So here you need to do something intellectual, but overall it's just implementation problem. Let's look at some of your solutions. Oh, yes, basically the same. Yes, just you even sort the array is the same. Okay, you break here, so that's a small difference. You can break. So I after you find the negative profit, you can just break. So that's it. That's problem B. Let's go next. Yeah, okay. Let's go to problem C. Problem C is, okay, so it's some strangely looking constructing problem, but it's actually really simple. So you need to understand what people want you to do, and you need to do the following. You need to build a square matrix n by n, and so with two purposes. In each row, you have numbers in increasing order, and you want to maximize numbers in column number k. Yeah. Well, and it's kind of trivial what you need to do. So you have in a matrix, if you want to maximize numbers here, then you kind of want to put the maximal elements here. So you want to make this element maximal possible. Yeah. So but all these elements to the right must be greater because each row is sorted. So all these elements are greater. So you can put some number of maximal elements in this row. Yeah. So you start from the last number, from n square. Then you have n square minus 1 and so on in decreasing order until you put the maximal possible element here. And then you start from the next row and again put the next maximal element here and so on. And so on. So every time you put the maximal possible element in each of these positions. And then fill the left part anyhow, actually. And you, again, if you think about this idea, you can go and see the examples. Yeah. Code force really slow today. I don't know what's happening. So, and you see that it actually looks like what you expect to think. Yes. So if k equals 1, then you want to put maximal elements in the first column. So you put 16, 15, 14, 13. Then again, start from the maximal, put them here. Yeah, so that's kind of what you expect to do. Here the k equal to 3. So you want to maximize elements in this third column. Yeah. So you put maximal elements here, and so to make things more interesting, the authors shuffled rows in this matrix just not to spoil the idea, but if you're smart enough, you can see the idea already. So you can put 3 maximal elements here, then start from 22, you put them here, then start from 19, put them here, and so on. Yeah. So again, each of these elements is maximal possible element. Yeah. Okay. So that's it. That's the whole idea. Now we just implement it. I didn't implement from the first try. I actually failed. You will see. So it doesn't look correct. Yeah. Okay. No, because here. Yes. Okay. No, so that's the correct solution. Okay, it's hard to see it from here again. Let's copy again from here. Okay, so we do exactly what I told you. So we go row by row, and we put maximal possible elements from right to left. So here I do exactly that. So I try to write the code the way I think about the problem. Yes. So I go row by row. In each row, I go from right to left. Yeah. So I go from the last position to position k. Yeah. No, count it from 0, so it's to k minus 1. Yeah. So I go from last position to position k and put elements in decreasing order. I just do it like this. So I put element n square and then decrease it by 1 every time. Yeah. Then I fill everything to the left. So I go row by row, go from position k minus 2 because I filled to position k minus 1. Now I start from position k minus 2 and fill everything to the left. Again, in the same thing. And you just output the result. Okay, so after you actually learned what you need to do, the rest is actually pretty straightforward. So its implementation is very easy here. The only thing you need to understand what you need to what the problem authors want you to build. After you understand what you need to build, everything else is kind of simple. Sometimes you also have some strange corner cases, but not this time. This time, actually, no corner cases in this problem. Just need to implement what you expect to be needed in this problem. Okay, I don't think it will be fun to read your solutions. So problem is too simple to read your solutions. So let's go to problem D maybe. Okay, problem D is actually fun. I was planning to make a special contest about trees, and we will do it in some point. Yeah. So that's nice problem about trees actually. I was thinking about saving it to another contest, but just decided to give it here. So what we need to do? We need to basically we need to reroute the tree. So we have a tree. Let me draw. So we have a tree. Let's look at the example. Okay, do we have examples? Too slow. Okay, let's look at this example. So we have a tree of 6 nodes with root. Initially, the root is in node number 2. No? For each other node, we know its parent in the tree. So we know the node which is one position closer to the root. Yeah. So for node 1, it's 6. So we have node 1, and its parent is 6. For node 2 we skipped. For node 3, it's 1. For node 4, it's 2. For node 5, it's 4. And for node 6 is 2. Yeah. So we have 3 like this. It's pretty boring tree actually, but yeah, good enough. And now we try to reroute this tree. So we try to change the root from the initial root to some new root. So this is R2. Yeah. And when we change the root, we have the same tree, But all these pointers now move to slightly different directions. So this pointer, for example, from 2 will point here. So we do this, and then output output the results. So for all nodes except the root, we need to output which node is the parent in the tree. Yeah. So in general, it looks like this. You have some big tree, something like this. And every node has point to the parent, like this. R1, yeah. Then you take node R2, let's take it, for example, here, yeah. And you just make this node the new root. And now all the pointers are now pointing in the direction of this new root, yeah. So this will be pointed in this direction, this will point in this direction, everything else stays the same, yeah. How would I solve this problem? I would just solve it in the most naive and simple way possible. I will just read this data, make a normal graph out of this, and then call the depth of search and build a network point. So I kind of move from two different representations of the tree. So there's one representation when for each node I know the parent, so I know this. Let me show you. So initially for every node you know the parent. So from this representation, I make like the general undirected graph. So I make undirected graph, like you normally do graphs. Yeah, and then from this undirected graph, I take the new root and call DFS from this root and direct all the edges in direction of this DFS. So I call DFS, and when I go, I make these pointers in this direction. Yeah. So that's the plan. So you go from this representation to this representation, and then back to this representation, starting from different node. Yeah. Okay, that's the plan. Okay, hope it's clear enough. If it's not clear, ask me, please. Let me show the code is pretty simple. Okay. Let me show. Okay. Stop. Okay, I'll just show you it here. I'm too slow today. No. Oh. I'm very slow today, I'm sorry. Something with the weather today. Where is it? Here's it. Okay. So here is it. Again, let me shoot you. Boom. Oh. So that's the plan. So initially, I read the data here. And when I read the data, I make the graph. So I have normal, like the most normal representation of the graph. So for each node, I have the list of the neighbors. Yeah. So when I read some number x, like the parent, I put both these. So I put this edge to both ends of this. So I can make unidirectional graph. Yes. So I make an edge from I to x and from x to I. Yeah. So I kind of move pointers in both directions in some sense. Yeah. So from one, so you have like two pointers. You have here and here. Yeah. And then I run DFS. Here I run DFS. DFS on tree I usually write like this. So I don't make marks. So in normal graph you will have array of marks, and then you mark the nodes you visit, and you don't visit the same node multiple times. Here I just when you make DFS on trees, you can just pass an additional parameter, which is the parent of this node, and just make it like this. So you don't need any marks. So you just visit all the neighbors except the parent. Yep. And when I do in this DFS, I also fill the array of parents. Oh, that's it. And then output it. Sorry. That's it. That's the whole solution. So it's just basically exercise on tree transformations, I would say. So you need to learn how to transform trees from parents array to graph and back. Again, many people solve this problem. I believe all the solutions are kind of similar to mine, so we don't read them. Okay, no questions right now. Okay. Where is everybody? Okay. Some people even left. Okay. We didn't have that much students today, but now we have even less. Okay. Oh, problem is actually fun. I like this problem. So what's happening in problem E? You have the following situation. You have a circle. Let's say from 1 to like this. And you have two operations. You can move all people by some number of steps counterclockwise or clockwise, so it's all specified here. And you also can so there are two operations. You can either move all elements, make a cyclic shift basically of the array. And the second operation is fun. So second operation is fun. In the second operation, you swap elements in pairs. So you swap elements in position 1 and 2, 3 and 4, and 6 and 5. So you have two operations. One operation is just cyclic shift of all elements. And second operation is swap of these pairs. Yes, question is just to simulate all these operations and find the state of the array in the end. Very fun problem, actually. So I believe there are multiple ways to do it. The way I did is like this. So first of all, let's think about the first operation. So if you only have the first operation, it's actually a very simple problem, yes? So what you need to do, so you have some numbers 4, 5, 6, and you only allowed to move them, let's say, clockwise by some x. No, in this here you allow to move counterclockwise, but it's actually the same, yes? So if you need to move them by -2, it's just the same as moving them by 4, yes? Doing this like by example. So if you need to move them by -x, it is the same as to move them by n-x, yes? So you can always do just positive rotations, doesn't matter, yeah? So imagine you only have cyclic shifts. Then it's not a big problem to find the solution, yes? So you just need to remember which cyclic shift you have now, yeah? So how to find which cyclic shift you have? For example, you can remember so you can fix some point of the cycle, like this point, and only remember the position of this point. Yeah. So imagine you know the position of 1 in the final array. Yes. Then you can easily find position of all other elements because you have some cyclic shift. Then you know that 2 must be here, 3 must be here, 4 must be here, 5 must be here, 6 must be here. So if you know the position of 1, you can easily find the positions of all other elements. Yeah. That's how you solve problem with only cyclic shifts. So you remember which cyclic shift you have. Cyclic shift is just one variable. So it's basically which shift is now. Second operation is fun. So it moves elements in different directions. So let's see. So the second operation does the following. So it moves element 1 to the right, element 2 to the left, element 3 to the right, element 4 to the left, element 5 to the right, element 6 to the left. Yeah. It's not a cyclic shift anymore. But since you already know how to solve cyclic shifts, you think, okay, is this situation similar to cyclic shift in some way? And you may, so after you draw this picture, you may actually see that it's actually very similar to cyclic shifts. So if you look at these elements like 1, 3, and 5, yeah, they all move in the same direction. Yeah. So kind of every operation does some cyclic shift on these elements. And elements, or even elements like 2, 4, and 6 also move in the same direction by the same distance. Yeah. So these three elements always move together, and these three elements always move together. Yeah. So what we can do, we can solve the same problem for these different halves of elements. So we can solve the problem for all odd elements and for all even elements separately. Yeah, because for each half of the elements, they move all together by some cyclic shifts. Yeah. So instead of one cyclic shift, you now deal with two cyclic shifts. So you have some cyclic shift of even elements and some cyclic shift of odd elements. Okay. So let's do it. Let's do this. What I will do, I will keep track of elements 1 and 2. So I know the position of element 1. So let's actually let's, for example, okay, let's look at the second or the first example. First example is fine. So I have 6 elements. Yeah. So I keep track of element 1 and element 2. And I have something here, something here, something here, something here. So I keep track only of these elements. So initially they stay in position 1 and 2. Yeah. Now I make cyclic shift of distance 2. So they move here. So 1 moved. 1 is moved here. 2 is moved here. Yep. Then I make second operation. Yeah. In the second operation, I swap these elements, swap these elements. Okay, let's swap them. So 1 goes here, 2 goes here. And then I make another shift by 2 positions. So 2 goes here, 1 goes here. Yep. So now we know the final position of element 1 and final position of element 2. And this information is actually enough to find position of all other elements, because you have cyclic shift of odd elements, cyclic shift of even elements. So look at even elements. You have 2, then here you must have 4, here you must have 6. Yeah, we have 1 here, so here you must have 3, here you must have 5. Yeah, that's it. So now you know the positions of all elements. Yeah? So that's it. So the idea is to keep track of positions not of all elements, but only of 2 elements, because these 2 elements define the positions of all other elements. Okay, here. So let's see what we have here. So A will be position of 1, B will be position of 0 or of 2. Yeah. Now I read all the queries. If query 1, I just make cyclic shift, just move both elements by x positions. See, I make plus n because I have because I don't have negative elements here, so x may be negative. So I make plus n to make a rectangle. Only 2 elements, because the position of elements 1 and 2 define position of all other elements. So back. So if you look at position at elements 1, 3, and 5, they all move together. So first operation just move all elements by the same cyclic shift. And the second operation swaps element 1, 2, 3, 4, and so on. Yeah. So elements 1, 3, and 5 will move in the same direction. Yeah. So both operations move elements, all odd elements by the same shift. Yeah. So you always shift elements with odd indices by the same amount. So they always kind of stick together. Yeah. So that's why if you know element 1, you know the position of all odd elements. And same with even elements. If you know position of element 2, you know position of all even elements. That was the plan. So that's what I'm doing here. So I just move both elements by x. Yeah. And here I do swap. So yeah, this is XOR 1. Okay. It's just cheating way to do what's in to do. So XOR 1 basically what it does. So okay. So, yeah. Now I need to explain my cheating. Okay. Again, let's look elements. So I have elements like 0, 1, 2, 3, 4, 5. Yes. So I have indices starting from 0. So 0 is basically 0, 0, 0. It's 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1. Yeah. So if you do it XOR with 1, yes, like here. So you change the last bit of the number. So you by XORing 1, you get 0, 0, 1, and from 1, you get 0, 0, 0. Yeah? From 2, you get 0, 1, 1. From 3, you have 0, 1, 0. Yeah? So you kind of swap these elements, and so on. So XOR 1 is cheating way to swap pairs of elements. Okay. You can write if here instead. It's not a big deal. I just like to do it in this way. And then now, when I know positions of 1 and 2, I just reconstruct the whole array here, just like this. So I start from position A, and with step 2, put all odd elements. When take position of element 2, and with step 2, see, put all, okay, I will change it to 2, so all even elements. Yeah. That's it. So, and now output result. Fun problem. I actually had a lot of fun solving it. I love them problems like this when you have some strange operation and you need to find a way to carefully simulate this operation. Just simulation, basically. So nothing strange happening here. You just need to simulate some process, and you think about a way how to do it fast. Okay, who's the first? Okay, you're the first. You get so that's something. So you get shift of all even elements, shift of all and total shift. Okay, and you check. Okay, so again, so I got it. So you basically you have even elements and odd elements, and you remember which elements are in odd position, which elements are in even positions. Okay, a little bit more complicated. Okay, so when you swap, you kind of swap all even and odd elements, and then adjust all the shifts. Now also doable, a little bit more complicated, but yes, okay. Nice formula. I and 1 XOR all shifts and 1. XOR swap. That sounds cool. I'm not sure I understand what's going on here, but we see which shift we need to use: odd elements or even elements. Okay, that's overcomplicated but beautiful, I would say. The whole solution basically is a simulation of operations. Yes, just basically simulate the operations not on all elements, but only pick 2 elements and simulate all operations only for these elements. And in the end, reconstruct the whole array based on these 2 elements. Yes, that's my idea of the solution. Here's a little bit more complicated. So you kind of you figure out that the current position can be represented as like couple of shifts. So and you just find a way to recalculate these shifts. A little bit more complicated to think like this, but also doable. Yes. Okay, let's move next. Then we have problem F. Oh, Robin Good. Problem Good is binary search problem. So last week, okay, not last, 2 weeks ago, we had a contest about binary search. And today we have binary search problem to test if you learn something. So basically what we have in this problem, okay, I will draw a picture here. So I have some here, if you sort all the people like here, you don't need to sort them actually, but if you sort them, what you're doing, you take some coins from richest people here and give this coin to the poorest people here. Yeah. Sometimes it's possible that they will intersect. So sometimes in the middle, these richest people become poorest people. It will happen if we ignore this fact for now. Yeah. So if we ignore the fact that these richest people may be poorest people after some number of operations, then this picture actually shows you that it's actually not that difficult. Yeah. So you just take some money from the richest people, give this money to the poorest people, and need to find this difference. You see. And the only thing you need to think, what is the maximal amount of wealth? Okay, what is the maximal wealth minimal wealth you can get here, and what is the maximal wealth you can get here? So to find these two levels, you can do binary search. Okay. Then you think, okay, what will happen if these richest people become the poorest people? But if this happens, it means that all your people have the same amount of wealth actually. So when it happens, so you decrease amount of wealth for richest people and increase for the poorest people. And when they meet, they will stay together. Yeah, so that's what will happen. So I will just check in the end. So if these two levels will meet at some point, then I will just output 0 or 1 depending on if it's divisible or not. Quite simple actually. Let me show you. So this is binary search. So this is normal binary search, the same binary search I use always. So I will use it twice to find the upper level and lower level. Okay, so here I find the upper level. So I find the number such that it's possible to make all wealth be less or equal on this. Yeah. So I basically just only take money. So I will not give money. I only take money. So I take money for some richest people and find the minimal possible level I can get. Yeah. Here I test level M, see how much money I need to take to achieve this level. So for every person who has more than this, here it should be maximum. I will fix it later. Yeah. So I see how much money I need to take from every person. If it's less than K, then it's possible. So R is possible value, L is impossible value. That's it. So I found the upper level. Now I will just copy it and do the same for the lower level. Now I only give money. Basically the trick is here to split the operation. The operation is tricky. So you take one coin and give one coin. It's too complicated. So let's split it. So we took K coins and then give the K coins. Yeah, it effectively does the same. Yeah. Yeah. So here just do the same, but now L is impossible, R is possible. No, L is possible, R is impossible. Yeah. I want to give coins, so every person get at least L coins. It's always possible to give at least 0. Yeah, and it's impossible to give everything a billion. Yeah. So here I put the middle value, check how much money I need to give to achieve this, and if it's less or equal in the end, it's possible. If it's more than K, it's impossible. Now I check in the end. I check if these levels do not meet, then it's just different of these levels. It means the situation didn't happen. So the richest people are still the richest, poorest people are still the poorest. So these two levels they didn't meet. Yeah. If they met, then I check if the sum is divisible by the number. If it is divisible, then it is 0. If it's not divisible, then it's 1. Like this, yeah. So after these levels meet, I have all people have the same wealth, yeah. After that, if the difference is 0, it stays 0. If the difference is 1, it stays 1. Yeah, because you take one coin, give them, so it's impossible to get difference equal to 0. That's it. Then I have mistake. Okay, here should be maximum. Yes, that's the mistake. That's basically it. So this problem about binary search. Just make 2 binary searches to find this border and this border. And again, the trick is to split operation in 2. So instead of having operation transfer money from here to here, you have 2 operations: take money and put money. Yeah, and now you kind of simulate. You can simulate them independently. You simulate these operations, simulate these operations. Yeah. And when they start interfere with each other, when you have okay, so if these 2 levels not meet, then this separation is kind of independent. You take money from here and put them to here, so they do not depend on each other. Yeah? And when we start dependent, it means this levels just met, and then it's just the answer is trivial. Let's find your mistake actually. So let's curious what mistakes you have. Do you have binary search? Oh, that's too hard. That's too complicated. So I believe you try to do the same without binary search. Yeah, but it's too complicated. I don't want to debug this. It's possible to do it without binary search. Yeah. I'm not ready to debug this right now. Too complicated. Too complicated. What's the question? You have 10. So it's 1. Yes, 10 doesn't look good because the initial difference is less than 10. You think it's GPT generated? No, it doesn't look GPT generated actually. No, it looks okay-ish. Okay, the problem is you choose too complicated solution. That's that's always a problem. So when you see some task like this, okay, so you get some solution, and sometimes your solution is too complicated, and you never know if you need to find the easier solution or you just implement what you think. Here I believe you chose too difficult solution. That's the problem. But at least you tried. Okay, that's good for you. Okay, so did you solve the binary search? I want to find someone binary search. Come on. Okay, that's binary search. That's what I love. Okay, so that's something I love. So here I have binary search to find this. Here I have another binary search to find this. This looks overcomplicated, but okay. Okay. So you do it. Okay. So you do it like this. You first take all the money, then adjust your array. Like if you took all this money and then you give this money. Like in 2 operations, take all the money, then give all the money. At least that I think that's what's written here. Okay. Also possible. Good. Let's move next. So we have 2 problems left. Okay. I didn't pause the video. Okay. Do we need this video actually? I don't think we need this video anymore actually. Let's just show you what's happening here. So problem G. another tree problem. So so in competitive programming, there are a lot of problems about trees. So if you're good at just operating with trees, you probably have an advantage. In this problem, we have another. So we had already one tree problem, and here we have another one, which is kind of more difficult than this. What we have in this problem? We have some tree, and we need to put some numbers. Let's put some. Let's move something. Yeah. And we need to put some numbers in the leaves. So for each subtree, so if you have two children, some of these subtrees, so some here and some here, must be the same. So you see, so for example, let's look at this picture. So in this picture, we have, so this element has two children. Yeah. So if I put some x apples here, here I have some 2x apples. Yeah. And if I put some number of apples here, like y, and y, here I have 3y apples. Yeah. And now these sums must be equal. Yeah. So it means that this sum must be divisible by 2 and divisible by 3. Yeah. It only happens if the sum is divisible by 6. So both these numbers must be divisible by 6. Okay. Let's put something here. I don't know, like some 3 and 3 here, and some 2, 2, 2 here. So we have some 6 here and some 6 here. Yeah. Let's actually put some more. Let's put some 6 elements here and 4 here. Yeah, so sum is 12. Sum is 12, sum is 12, so total sum is 24. Yeah. Now for this element, I have something divisible by 12 here, something divisible by here. So this sum in this must be divisible by 12. Yeah. Makes sense. Yeah. So again, if you do anything with this subtree, this number will always be divisible by 12. No, why? Because it has two children, and in both children, the sum is divisible by 6. So, so this sum is always divisible by 6. This sum is always divisible by 6. So the sum should be divisible by 12. Okay. Now, if in this leaf you have something like 24, here you have like 20. Yeah. So in this leaf, you also must have some which is divisible by 12. Yeah, because sum must be the same in all leaves. Yeah. The closest number divisible by 12 is 12. So you can reduce this number to 12 and then reduce this number to 12. Yeah. Okay, let's a little bit messy. But again, the idea is that for each subtree, we know that the sum in this subtree must be divisible by something. Yes? And then we'll try to adjust. Yeah? So if you have several subtrees, some here is divisible by A, some here is divisible by B, some here is divisible by C, then all these sums should be divisible by LCM of A, B, and C. So that's what I will do. So I will calculate for each subtree. I will calculate the maximal sum I can get for this subtree and this divisor. So I know that the sum of the subtree is x, and it should be multiple of y. So I will, for each subtree, calculate two values: the maximal sum I can get for this subtree and the number I need to be divisible to. And then I will combine these numbers. Okay. Let me show, actually. Video is boring. Let me just show you the code. Copy, copy, copy. Okay, so code is pretty short actually, so it's like 60 lines. Okay, it's intense, but it's short. Let's see. So again, here I just build in the graph. Yeah, so that's just normal start for my program about trees. I read all the edges, put them in this list. Now I have basically graph. Yeah, and then I call DFS. So yes, so DFS again will be for the vertex and the parent. And in this DFS, somewhere in the middle, I make a recursive call here. So I make a recursive call for all the neighbors except the parent. So this is basically normal DFS, but I had a lot of extra stuff here just inside the DFS. You can do it separately, but I just do it inside the DFS. But overall, it's normal DFS. Yes, so I run it. So I give it vertex and the parent, and here I make a recursive call for every neighbor which is not a parent. So yeah, so I make this recursive call plus something else. It's actually no, it is just biased, so it's perfectly random contests. I usually pick problems by as random as possible. There are just too many tree problems on Codeforces because it's very popular topic. Not only in Codeforces, just in competitive programming in general. People love problems about trees, basically because they are solvable. So if you take the same problem for graphs, they usually unsolvable. But for the trees, you make some DFS of a tree, calculate something, and you're done. So that's why people love trees, because a lot of problems are much easier on trees. Let's go. So what we have? So I iterate all children, and here I calculate. So this table. So this result will be this thing. So it will be the maximal sum I can put, and the second element is the multiple. Yeah. So again, let's go here. So if I have no children, so if nothing happens, rest is still -1. So if it's still -1, I will put the following. So this is all for the leaf. So for the leaf, the maximal sum is just an initial sum, and the multiple is 1. Yes, I can put any value in the leaf. Yeah, any value multiple of 1. So all numbers are multiples of 1. Yeah. Now, if I have some children, so I will take these children one by one. If it's the first child, I just put it here. I believe I could simplify this, but I didn't. So I just put it here. And when I take the second child and the following children, I merge these results. Yeah. So I have some value here, some value here, and I merge them. So I merge them. So second value is just LCM. Yeah. So now the values should be divisible by this value Q. Now I make this value divisible by Q by subtracting the remainder. Yeah. So this is one way to make the number divisible by Q. So you decrease the number to the closest divisible by Q. You can do it like this also. You can do it something like divide by Q, multiplied by Q, something like this. That also works if you prefer. Yeah. So you can divide by Q, then multiply by Q. You have the closest number divisible by Q. Then I calculate the minimum. So I do it for all the children. So now I know this lowest common multiple. Yeah. And for every child, I know the maximal value I can get in these children. Now, I need all these values be equal. So I take minimum of all these values. Yeah, and this is my result. And here I do this cheat because I don't want to have zeros. Sometimes this LCM may be too large, and to prevent this LCM being too large, if LCM is large, then the value just be 0. So when I see 0, I immediately put second to 0 because everything else will be also zeros. Okay, so this is just cheat to. You should put 1 here actually. Okay, to eliminate this problem. Okay, so this is just cheat to avoid overflows, because when LCM overflows, you have some strange results. Yeah, but if LCM overflows, it just means that your result is 0. So if all the numbers should be divisible by a large number, it means they all should be zeros. Yeah? And that's it. And then I just multiply by number of children. Yeah? So I count how many children I have here and multiply by this. Hard problem actually. So it's short. Solution is short, but it's really intense actually. So what's happening here? It's very intellectual part. So it requires actually some experience in number theory and in trees dynamics or something like this. Let's. I wanted to read actually your solutions. I don't think you have something much different. Okay, you have solved this problem in the same minute. Okay, so let's read yours. I'm not sure I don't know what happened to code forces today. It's just very slow. Okay, this is LCM. In modern C++, there is a special function LCM. You don't need to do it like this anymore, actually. Interesting. You don't have this problem with overflows. Why? Okay, I'm not sure I understand what's going on here. But you somehow avoided these problems for LCMs. So vals and val equal this. You fix it like this. So this is your fix. So just when you have overflows, you just put 1. That's actually a fun way to do it. Okay. So this is how you avoid overflows, basically. Yeah. Was it your mistake in the first submission? You have runtime sync to overflow. Yes. Okay. So this was your mistake, and that's how you fix it. Nice. So I usually don't like to have integer overflows, but you just intentionally make overflows, and then if it's negative, you make ones. Okay. Okay, now let's go to the last problem. Okay, I will not show you my code. My code is terrible. So my video. Again, I spent like an hour solving this problem. I will not show you whole hour of me suffering. Actually, the most of the time I was just thinking if my solution is too complicated, maybe there is easier solution. Later I read the tutorial and it turns out it's actually what authors expected from this problem. Okay, let's go. So now what we have in this problem? Basically we have my favorite type of graph. It's functional graph. So when every node has only one outgoing edge. Yeah. So here we have it in form of a table. So we have a table. Yeah. And for every cell of this table, we have, so if we stand in this table, in this cell, we know where we will move. So we'll move here, from here we'll move here, from here we'll move here, from here move here, let's say. Yeah. So for every cell, we know where we will move if we go. From some cells, we don't move anywhere because we can't move. So if it's out of the border of those, when we just stay in the same cell. Okay, so this is something called functional graph. And in general, it looks like this. It has some cycles. And maybe some simple cycles like this, maybe some loops like this. So the core of each component is a cycle, and then we have some ingoing trees like this. And something here, and something here also maybe. Something like this. So each component of this graph is a cycle. It's like core of this component, yeah? And then we have some ingoing trees for this component. So graphs like this occurs in different situations, and especially in competitive programming, sometimes they just give you a graph like this. Sometimes even in general, there are situations when you need to analyze graph like this. So this graph, what's interesting about this graph, it's almost like a tree. So it's basically like tree plus infinite loop in the end. So when you think about these graphs, you think basically the same like you will think about trees. Yeah. Okay, let's keep it in mind. So the first part of it just okay, the trickiest part for me was just to figure out that you need to build all this picture and just build it carefully. I made a lot of mistakes just trying to figure out. So what I will do, for each component, I will actually build this structure. So for each component, I will find these cycles. So for each component, I will build this cycle. So we have some cycle. Just find all the cycles. That's already a fun problem. So if you didn't do it before, it's fun thing just to find all the cycles. It's not hard thing to do. It's just simple DFS over these trees, but it's fun. Just try to do it if you didn't do it before. And then to this cycle, there are something connected. So basically, I would build this rooted tree, but instead of normal root, I have the cycle. So I will build these components and then run some tree algorithm for these components, basically. Yes, again, we have kind of tree problem. It's not exactly tree, but something similar here. Now to the problem. So what we need to do? So we have a string, and we need to read the string by going through this graph. So we start in some node of the graph and walk. In every node there is one digit, and we can take this digit or skip this digit, and we need to read the given string. Okay. If you I hope you read this problem before, so it's kind of clear for you what's going on. I don't want to explain you the problem statement that long. So let's go to the solution. So so this is the first part of the problem. So trying to understand how the graph looks like. Graph looks like this. Yeah, it's almost tree, but with cycle. Okay. Second part of the problem. Reading the string. So imagine you have some string. Like have like 239. Yeah. And you want to read the string. So you have this you start from some node, go somewhere, go somewhere, go somewhere, go somewhere, and so on. Yeah. And then you have infinite loop. Yeah. And you wanna read the string. How do you read the string? You do it greedily. Yeah. So you start from this node, and let's put some digit here, like digit 1. So digit 1 is not 2. You need to start from 2. So you skip digit 1. Yeah. Then, for example, have digit 2. So digit 2 equals to this. So you take this digit, move the pointer here. Now we're looking for digit 3. So it's like greedy. You do it greedily. Yeah. You're looking for the first digit, then you're looking for the second digit, looking for the first digit. Or you may think about like 2 pointers method. So 1 pointer is here, 1 pointer is here. Yeah. So if you have the same digit, then you move the pointer. Yeah. So it's like finding a subsequence. Yeah. So when you look for subsequence, so again, you have some string and you find some subsequence. You look for the first element, then you look for the second element, then look for the third element. Yeah. The same thing happening here. I go along this path and greedily find all the digits I need to have. Now, since I have this structure, so usually, so in this graph, I go along this in this direction. But in trees, it's actually easier to go another direction. You go in DFS on tree, you go from root in this direction. So let's try to reverse everything. Let's try to reverse direction. Let's try to go from cycle in this direction. Can we do it? No, yes, we can. We can just reverse the string and go in opposite direction. Okay. No, that's basically it. So the idea is like this. So you have some string. You start from the cycle. So you can make infinite number of loops along this cycle. So this cycle will take some of the digits. So you already found some digits walking along the cycle. Yes. Then you go out of the cycle. And then you go along some path in a tree. Yeah. And when you go along this path, you go greedily. Yeah. So you go, if you have the same digit, you move to the next digit. If you have different digit, you just skip this digit. Yeah. So you can do it using basically simple DFS. So every time you go to the node, you remember how many digits you already read. If it is the same digit, you use it. If it's different digit, you skip it and just continue your DFS. Let's have some example. It's actually really difficult problem. So let's have some example here. So imagine you have some cycle with digits, let's say 2, 1, and 5. And I have something here. 1, 4, 7, and good enough. And 2. Oh, something like this. Yep. And you need to read some string. Let's say what? Let's say 8, 4, 2, 1, 1, 5. Yep. So what we do? We first read everything we can read from this cycle. Yeah. So we read this part. So we read all the digits which we see in the cycle. So these digits we can read from the cycle. Now we need to read all the rest from some of these trees. So we do DFS. We go to this node. Yeah. When we visit this node, we have in this position. We check if this digit is the same. No. Yeah. It means we cannot read this digit. So we just continue having the same position here. Here we have the same position, 4. Yeah, or same digit. So we can read this digit and move deeper in the tree with looking for the next position. So now we recursively go to this node looking for this digit. So we in our DFS, we pass the index of the digit we're now looking for. Yeah, and if we have the same digit, we just move this pointer to the left. Yeah, so when we didn't find anything, so we move back, go here. Yeah, so now we stand in this vertex, and again we look for this digit 8. We don't have digit 8, so we continue forward, and here we find digit 8. So we skip, we take this digit, move this pointer here, and now we see what we write the whole string. So basically, it's greedy algorithm inside the DFS. Very difficult problem, actually, very difficult problem. So let's read the code. Maybe it would be easier to understand. Okay, so this is the idea. So here I just read the data. Here I just transform my strange input to normal graph. Yeah. So instead of having this table with all these different vectors moving, I just have normal graph. So I have this array P of the pointers where this was moved, and that's it. So yeah. Now here I try to find all the cycles and build these trees. Here I made a lot of mistakes actually this time. I need to learn how to do it easier actually. So what I'm doing here, so this is normal algorithm, normal DFS for finding cycles. So you mark 1, you make mark 2. If you visit some neighbor with mark 1, then you have cycle. Just very default algorithm for finding cycles in graph. It doesn't know that the graph is specific. It's just general algorithm for finding cycles actually. When I find cycles, I mark this cycle, put it in an array. So I have an array of cycles. Yeah. If it's not cycle, if it's not marked, I run DFS. Then if my node is not in a cycle, I make this pointer. So these pointers are for my future tree. Yeah. So I will have cycles plus trees. Yeah. For every cycle, I have some hanging trees. So this array G represents these hanging trees. Okay. Now I just solve here. Okay. Very complicated. So first you need to skip everything which you have in a cycle. So you take the cycle, see which digit you have in a cycle. Now for each digit which is not in a cycle, you find the rightmost occurrence. So see, so I want to find this digit 4. Digit 4 is the rightmost digit which is not in the cycle. So that's what I'm doing here. So I take all the digits. For each digit which is not in the cycle, I find the maximal rightmost occurrence. So now M is this rightmost digit. So it's rightmost digit which is not in the cycle. If it's -1, it means I have all digits in the cycle. Answer is yes. Ta-da. Easy. Yeah. If it's not, I look at all the trees connected to my cycle. So I iterate over all nodes of my cycle. For each nodes, iterate over all children. See it? So I look at everything connected to this cycle. Okay, I could just run DFS from X. Okay, doesn't matter. Okay, run DFS. Second DFS. It takes the node and the position in the string. Yeah, it greedily takes this position if it can. So if I can take this position, I take this position and move it one position left. Yeah. If it's -1, it means I found all the digits. I return true. Okay. Then just call it. It's just normal DFS. That's basically it. Very long problem. So it's like more than 100 lines of code in just intense code. So it's difficult problem. Yes. I want to show you actually. Do we have time? Oh, we have time. I want to show you how I actually debug this code. So when I first, you may see here, so it's my first submission was here, so I spent a lot of time just debugging this code. And so first few mistakes was kind of easy to find, but later on it was more and more hard to find the mistakes. So how I find these mistakes? So sometimes I just read the code. So you can just read the code and find the mistakes. But the last few mistakes were actually hard to find. Let's copy. Pop. So this is code with mistake. It looks kind of the same. So somewhere here, I made some mistake. And when you have code of this size, you have like, and even longer sometimes. So it's not the hardest problem you can see in the contest. You may have like 200 lines, 300 lines sometimes. Not in code forces usually, but in some long contest you may have much longer solutions. How to find the mistake? And the method that I usually recommend to everyone is stress testing. Stress testing is the most powerful thing you can learn for debugging. So if you have this problem, if you stuck in solution, you don't know where is the mistake. So I have no idea. So I can read all these 100 lines one by one several times. Probably at some point I will find the mistake. Maybe not. Can you find the mistake here? Somewhere is the mistake. So what you do? So instead of just looking at the code and slowly going insane, you do something constructive. Yeah. So you do stress testing. How stress testing works? You have your code. You implement another solution, which is this most stupid solution you can find. Yeah. So this is my stupid solution. So I kind of believe that this part was. So this part I just copied from the code. So this graph building. So I built the graph the same thing as. So it's hard to make mistake here. Okay. Now this part with all the cycles and stuff I just remove completely. And instead I make the simple greedy algorithm. So I read the string, try all possible start points, and from every point I make this number of steps. It should be more than enough. Yeah. So number of steps is not greater than size of the string multiplied by size of the graph. Yeah, because even if you have a long loop, size of the loop is at most size of the graph. Yeah. And if you have at least one character on every loop, then you have at most this number of steps. Okay. So I just simply simulate the process. So I make this number of steps, just a lot of steps. You can put some big constant here. That doesn't matter that much. I just estimate number of like this. So it should be enough. Yeah. And check if it is my digit, I skip it. So it's simple greedy algorithm without all these trees, without all these cycles. Just try every starting point, implement greedy algorithm. If you find, you find. So this is the most stupid. You can see that it's not that simple. Yeah. So because problem is complicated. Yeah. So even stupid solution is kind of complicated, but it's much more stupid than this solution. Yeah. So it's like again, it's like 60 lines of code, and okay, this code is actually trivial. Yeah. So most probably problem was here. So this code is much easier to validate just by looking. Yes. So this code is probably correct. Now I write a generator for the tests. I usually do it in Python because it's faster. Yeah. So I wrote this the most stupid generator of tests. Yeah. So I just take some small size, generate only one request because you don't need many requests to find the mistake. Yes. Generate some random matrix, generate some random vectors, generate some random string. Ta-da! Yeah, that's it. Okay, the most stupid possible generator. Just generate some random test. And then you just run the generator and run both your solutions, check the result is the same. I do it using this script. Okay, so script just compiles both solutions and run million tests. I don't know how to write infinite loop in Bash, so I do menial steps. Okay. It's supposed to be infinite loop, but I just don't know how to write infinite loop in Bash. Run generator, run both solutions, and this magic line checks that they are the same. So it's a simple call compare function, standard compare function from Unix systems. Yeah, compare this. If they're not correct, the return value will be not 0, so I will make this break. Yeah, so magic line which checks that two files are the same. If not, then break. That's it. Very simple script. And now I just run the script. I can do it right inside the IDE like this. So I call this stress, give it one solution, give it another solution, and it just runs. So it just runs. So it's generate random tests, run both solutions, check that they're correct, and you just run this, and you can go get some tea, sleep a little bit until it finds you right. So if your solution is wrong, then most probably you will find mistakes somewhere. Like here. So, okay. So after generating like 600 tests, I found the test which is incorrect. So you can see, for example, for this test, no idea why. Yes, your main solution gives no, and your stupid solution gives yes. Yes, and you can look at this test and see if it is actually yes. Look, and string is 1. String is very boring. Yeah, string 1 is definitely yes, because here is it. Yeah. Okay, so now you have a test which doesn't work. So it's much easier to debug. You just look at this test, see what's going on in your program, and find the mistake. Okay. Okay, I need to have special lecture about stress testing. Very important technique. So help you to save a lot of time and save a lot of nerves. Because when you just trying to find the mistake by reading the text over and over again, after like 3 times of reading that long text, you just you can think normally because you have it's a problem of context. There's too much context here. You can't load it in your brain. So you need some help of tools. Yeah. So that's it's just some automatization which helps you to find mistake. So again, after you have a test, much easier to find the mistake because you can look at this test, just print all the steps of your program and find at which point you make something strange, and then localize your mistake. That's the idea. So you don't need to look through whole your code. You find the local part which doesn't work and find mistake in this local part. In this code, I believe the mistake was somewhere here. So I believe you need to push it anywhere. So or here. Yeah. I need to add this edge even if it's not in the sex. So you just need to remove this if actually. I believe it's like this, yeah. Yeah. So you fix the mistake, run the code, run the stress again, go get some more tea or solve some other problems. You can run this stress test and go solve other problems. Yeah. And it's just working. So yeah. And if it passes like 1,000 tests or something like this, then you think, okay, maybe this solution is correct. Or maybe my stress is not enough. Maybe it doesn't work on this. So you may tweak the parameters here. So you think, okay, maybe for this small graph it works. So maybe I need to give it some bigger size of the graph or small, maybe some corner case. Yeah. So maybe I generate maybe the test I generate actually pass. So maybe it fails on some another test which I cannot generate. So you think about your generator and so on. But again, at least you're doing something. Yes. So you're not stuck in such just thinking what is the mistake. You're looking for mistake. You're doing something. Yeah. That's important. Okay. Hope you learned something new today. That's it. That was contest 5. Last problem, probably too hard for this type of contests, but again, you need to learn how to solve hard problems as well. Thank you for watching. See you next week.